All right. Um, how's everyone doing this afternoon? A couple of announcements. First of all, the grade stuff that was happening yesterday, that was an April Fool's joke. So I've deleted the April 1 extra credit. So you don't have minus, hey Jackson, minus millions of percent or plus millions of percent. Your grade is back to normal. All right, there was an item in the daily part of the daily item from yesterday was to draw something, and I realized that I didn't teach that to you yesterday, so I'm going to start off by teaching you how electric power is generated. Okay. So the basic idea is this. You spin a loop of wire in a magnetic field. That's how you make electric power. So let's suppose you have, like, I don't know, a U-shaped magnet. So you have a U magnet that has a north pole and a south pole. Okay. So the magnetic field lines go out of the north pole and into the south pole, kind of like this. Okay. And then you have a loop of wire. I'm going to make it a square loop of wire. Something like this. And the loop of wire is made to spin. Okay. And when you make the loop of wire spin in a magnetic field, you will have current flowing out of the wire and you'll get a voltage generated. Okay. Now, because there's electrical power coming out of the loop of wire, energy is conserved. So you have to have energy going in. So you need to, by the way, this is how a generator works. Okay. So you need to have some method of spinning this loop. It's going to take energy to spin the loop. Okay. So whatever is spinning the loop is basically, the source of energy that you're converting into electrical energy. So for example, if you had a wind turbine, the spinning propeller thingy on the wind turbine is connected to this loop. So every time the turbine spins, the loop spins. Okay. So you're using wind energy to spin the turbine. Okay. So the question is, what source of energy is spinning the turbine? Okay. For example, what about a coal plant? If you have a coal plant, it kind of looks like this. You've got basically you have a I don't know what you want to call it. You could call it a boiler. Yeah, let's call it a boiler. I think that's what it's called. And the boiler has some water at the bottom. And you're burning coal to heat up the water. This is supposed to be a flame, okay? You're burning coal to heat up the water. High sofa, high spicy pepper. And so what happens when you boil the water is the steam rises, okay? And as the steam is rising, you put a propeller in the way so that the propeller will start to spin, okay? And as the propeller spins, the propeller is connected to the loop that's spinning in a magnetic field. So you get electrical power generation. Now, of course, as the steam rises, it needs someplace to go once it hits the top. So you have some kind of like a output pipe. And then the output pipe goes next to some, so you have this steam, okay? The steam is kind of flowing this way. And then it goes through a region where it's cooled down. So that might be, you might run the pipe through a river or something so that the pipe exchanges heat, all the heat leaves the steam. The steam condenses back into water, and then it's fed back in. So you have this like loop of, so this is called the condenser. So you have this loop of you're boiling the water, you're turning it into steam. As the steam rises, you spin the turbine. The steam swings back around. It turns from vapor back into liquid water, and it is ready to be boiled again. Okay? So where are the inefficiencies in this process? Well, if you're burning coal, then not all of the heat is going to go into the water. Okay? So not all the heat is going into the water. Some of the heat is escaping into the surroundings. Okay? Similarly, the steam that rises, propellers aren't able to absorb all of the kinetic energy of the rising steam. Okay? Why is that? Well, if it absorbed all the kinetic energy of the rising steam, then the steam would just stop right there. So you wouldn't even have any flow through the propeller. It would just stop right at the propeller. So you have little inefficiencies built into this. This could also be a nuclear plant. Okay, where instead of burning coal to heat the water to turn it into steam, you're using nuclear fuel, the heat generated by nuclear reactions, to heat the water. So in this type of a power generator, the only question is, what are you using to heat the water? Is it natural gas? Is it coal? Is it nuclear? So your only option is, what are you using to heat the water? Okay. What about a hydroelectric plant? In a hydroelectric plant, you have basically the gravitational potential energy of the water. Becomes the kinetic energy of the water, which becomes, right, because the water falls and it turns into kinetic energy, which becomes the rotational kinetic energy of the turbine, which becomes electrical energy, which I'll just call EE. Okay? So this is a hydroelectric plant. For For a wind farm, you have the kinetic energy of the air becomes rotational kinetic energy of the turbine becomes electrical energy. Okay. And the way you turn the rotational kinetic energy into electrical energy is via this process of a generator. Okay. How could we figure out how much energy can we get? Well, if we think about, for example, a hydroelectric plant, the total amount of energy that we can get, it's coming from gravitational potential energy, right? So, and that's just mgy. But if we think about it, if you have a bunch of water that's behind a dam, the y value isn't the maximum height of the dam. It's actually the average height of the water in the dam. So I'll put a bar over that for average, where oftentimes that would just be the average height is just the maximum height divided by 2. It's kind of like if a pool is 10 feet deep and you wanted to know how deep is the typical amount of water, what's the average height of the water, you would use half that. Okay. And then we have to multiply that by the efficiency of the energy conversion process. And this would be the amount of energy you could get from a hydroelectric plant. So this is the gravitational potential energy of the water that's behind the dam. Okay. Another thing I wanted to talk about a little bit is solar energy. There is something called the solar constant, which is denoted by S, and it's equal to the power received from the sun divided by the area. Okay. So the solar constant is power divided by area. And so it's units. The units of solar constant are watts per meter squared, power per area. Constant for Earth is about 990 watts per meter squared. So if you had a 1 meter by 1 meter solar panel, the energy and you pointed it directly at the sun, then the maximum power you could get would be around 990 watts. Okay. This is the solar constant for the surface of Earth. If you were to go up into outer space, in outer space, we don't have an atmosphere absorbing some of the sunlight. So the solar constant is actually greater if you're in outer space. So a solar panel in orbit around Earth is going to be able to produce more power than a solar panel on the ground because the atmosphere absorbs some of the sunlight. If you were on a different planet, the solar constant varies from planet to planet. Planets that are closer to the sun have a larger solar constant. So at any rate, we can take this equation and we can multiply both sides by area, and we get power equals S times A. All right. So this is the maximum power that you could get from a solar panel, but solar panels are not very efficient. In fact, they're only about 10 or 15% efficient. So the power that you actually get is efficiency times solar constant times area. Okay. The efficiency is affected by things like, is the solar panel dirty? Is it using the most recent technology? Is it new or is it old? What is the angle of the sunlight hitting the solar panel? You want the largest, you want the sun to be shining on the solar panel directly, okay? The solar constant is affected by things like weather, okay? So at any rate, this is the energy you can get from a solar panel. I encourage you, if you have a house that has solar panels, to use this equation and try to estimate how much power can you get from your own solar panels. I was talking to my neighbor the other day because my neighbor just had, let's do an example. My neighbor. So I'm actually looking at my neighbor's roof through the window right now. And my neighbor has, her solar panels look like this on the roof, okay? And it looks like they're about 6 meters long and maybe, I'm gonna say, 1 meter tall. So the area of her solar panels are 6 square meters, okay? The solar constant is 990. And as I said, the efficiency of a solar panel is not very large. It's like 10%. So 0.1 is the efficiency. So how much power is she going to be able to get for using those solar panels? 0.1 times 990 times 6. That is a power output of 594 watts, which is 0.594 kilowatts. Okay, so 0.594 kilowatts. And how many, if we take power and we multiply it by time, we get energy. So how many hours are her solar panels getting energy for each day? Maybe 10 hours. So if we multiply that by 10, the total energy that her solar panels are going to output per day are 5.9 kilowatt hours. So I multiplied it by hours to get energy. Okay, so that's the energy in a day. How much energy is she going to get in a month? Okay. I'm kind of going on a rant here, by the way. So if I take this and I multiply it by 30, that's the number in a month. So I have 5.9 times 30. That's 177 kilowatt hours. Do you know how much a kilowatt hour costs? If you buy a kilowatt hour of energy from the electrical company, it costs about 20 cents. So if I take this and I multiply it by 0.2, that means that her solar panels are going to generate $35 per month. Okay? And so I was talking to my neighbor, and my neighbor is like, oh, I like to run the AC in the summer because, I get too hot in my house. and the electrical bill goes up to $300 a month. So I got solar panels, so I won't have to pay as much. And I wanted to tell her that, well, your bill is not going to go down by that much. It's only going to go down by $35, but I really just don't care. She'll find out soon enough in a couple months that it doesn't bring it down that much. Okay, that's all I have for today. Bye now.